just define the space constraint. And we'll do the anchor discriminator, which is 8. And then we have to be able to calculate how much space that it's going to take up. And that's going to be defined by what you're actually putting into this account struct. So one thing that we do need to specify is what is this vesting account going to be. This is a custom-made account, so we're going to pause from writing this data structure and we'll just go down to define what our vesting account is actually going to be. So on Solana, all smart contracts are stateless. Every state is stored within accounts. So here we're creating a vesting account that is going to store all of the information for a specific vesting smart contract. So what do we want to store? We're going to first define that it's an account. We're going to use the account macro from Anchor. We're going to name this vesting account. Okay. So this is a vesting account for an employer for all of their employees at a company. So what do we want to save here? First, we want to know who the owner is. So that's going to be whoever has special permissions to update the vesting account. So we'll save the owner, and that'll just be the public key of the owner. And now we're going to be distributing SBL tokens. So we want to save what the mint is for the SBL token. So that will also be a public key. And now this is just an account that's storing state. We're also going to need an account that's storing the SPL tokens. It'll be a token account. So we want to be able to store what the public key of that token account is within our vesting account state. So let's just do public key. We'll just do pub treasury token account. This is just going to be the treasury account of an employer's tokens that are all going to be allocated to employees that are working and receiving vested tokens. So this will be the treasury token account. The type will be public key. Okay, another thing that we'll want to store just for referencing, maybe creating a PDA in the future, is the company name. So we'll write company name. And that'll just be a string that can be a user input value when they're creating their new vesting account. And then we also want to save the bump, and we'll save the bump for both the treasury token account as well as the vesting account. So we'll do bump for treasury. And that's always a U8 type. And then just the bump for the vesting account, which is also a U8 type. So now we have the account, but how are we going to actually calculate the space? Anchor actually has a way to do that. So this account macro is an attribute applied to the data structure to designate that it's a Solana account. And then we can also add the derive macro, and it's an implementation onto this account data structure. And we can specify that we want to use a init space. So we'll just do derive and then a init space. And what this does is Anchor automatically calculates the space for you. Now you can see that when I wrote that, we have an error that was generated. And that's because the company name is a string value, and a string can be extremely long. So we're going to want to designate a max length for what this string can be. So I can just go in here and actually write max length. And I'm just going to say 50. Seems good for a name. Now that error went away, and now we have our account fully defined. So now that we have that, when we're calculating the space in our create vesting account struct, we can just use the init space. So that's going to look like just the name of the struct and then a init space. Okay, so now that we have the space calculated, we need someone that's going to pay the rent. So we just have to define who the payer is. And that's going to be the signer of the instruction. And now we're creating a new account. So since we want to be able to derive the PDA in the future, we need some type of attribute that differentiates the different PDAs for a specific signer. So here we're just going to use the company name. So we can do seeds and we'll use the company name as ref. Okay. And then lastly, because we have the seeds, we need the bump. And then we're going to just need to define what this account is. So we'll name it vesting account, and it will be an account with the lifetime specifier, and it's going to be using the vesting account struct that we defined right here. Now, there is an error, and the reason for that is because we're passing through a company name, and this struct doesn't know what it is. So yes, we need to update the input parameters from the instruction first and just say we're allowing on the front end someone to type in what the company name is. That'll be of type string. But this still isn't passed through down here. So to be able to pass this information through our context data structure, we're just going to add this macro that is basically saying we're pulling this variable from the instruction. So we'll do the instruction and then name the variable. So we're using the company name of type string. Okay. The next thing we're going to pass through is just the mint account, and that's going to be what the SPL token mint is for the vested token for this specific vesting account. And we're going to be using interface accounts here. And it will be a mint type. So we need to import this mint, and this is coming from our SPL token crate. So you can see here, anchor SPL token, mint. But actually, we're going to be using the token interface rather than the token. So we'll go down to anchor SPL token interface mint and import that. So you can see the import updated. And you can see the vesting account still has an error, and we'll get to that in a second. But basically, whenever you initialize a new account on chain, you do need to pass through the system program. But we'll pass that through towards the end. So far in our context data structure, we're passing through the signer who is signing the instruction. We're passing through the vesting account that we're creating to hold all of the state for the new vesting account. We're passing through the mint of the SPL token that we're vesting. Now, we also need the treasury token account that's going to store all of the tokens that are going to be handed out to employees. So we can initialize that at the time of running this instruction. So we're once again going to use the init constraint on the account. And now here, it's going to be a little bit different because it's a token account. So we're going to need all of the information for the token. We can do that by running the token constraint. And we'll define what the mint is for the token. And that mint is going to be the mint that we just passed through above on the previous account. Okay? And now we also need the authority for the token. And that authority is going to be the token account itself. So in the future, when we're actually transferring the tokens, the token account has the ability to transfer to the employees. So we'll set the authority to the treasury token account, which is what we're going to name this account. Okay. And now we just need the payer, which will be the signer once again. And then here we're going to define the seeds. This is going to be a token account, not an associated token account. This is because it's going to be a token account specified just for this vesting contract. So we want to create seeds for the PDA that will make it easy to derive. So we'll make the seeds. We'll make the seeds state that it's the vesting treasury, and we can do that by just typing out vesting treasury. And then we'll also want to add in the company name as ref. Okay, a little typo, let's fix that. There we go. And now because you specified the seeds, we also have to add the bump. And now all the constraints are defined, so we just want to state what this account is, and that will be our treasury token account. And now we're going to update this to an interface account. And then the type will be a token account. So now we have our treasury token account, our vesting account, we have the signer, we have the mint. So all that's left is two things, our system program and then the token program because we're creating a token account. And this token program is actually going to be an interface, and we're going to use token interface. And now you can see we have one more error left, and that is we need to import token account. So we'll just import that, and that's going to come once again from the token interface. Okay. And because we're using a string here with vesting treasury, we're going to update this. Instead of as ref, it's going to be as bytes. And that's everything for all of the accounts that we need for the first instruction to create a new vesting account. So now we can write the logic out for creating a vesting account. And you can see here, there's a warning generated for a company name, and that's just because we haven't used it yet in the logic, and Rust always wants to warn you if you're passing through a parameter and it's not being used. So the first thing we're going to do is just load in the vesting account, and we want to be able to update the state. So because the context holds all of the accounts for this instruction, all we can do is just load in the context dot accounts, and we can point to the vesting account. Now what we need to do is we need to dereference this. So we can add this asterisk, and that is a dereference operator in Rust. And what that does is it dereferences the account that it's pointing to, which is the vesting account in our case. And it allows you to modify the account. You need to do this because it's an account reference. You need to dereference it to be able to modify it. And this tells Rust that you want to work with the actual data and not just the reference. So now you can update values of the actual data of the vesting account. Now we'll just pull in the vesting account type. Okay, and then we can just update all of the fields within vesting account to save the information for the new account that we're creating. So first we'll do owner. And that will just be the key of the signer. So we can pull in the signing account and then just grab the key. Now we need the mint. And we'll just pull in the mint account and grab the key. Now we need the treasury token account. Once again, we'll pull in the treasury token account, grab the key. And then the company name is just going to be the company name that's passed through. And then we'll just grab the bump of both the treasury and the vesting account. Okay, sometimes Copilot tries to autofill things and it's not always correct. So we're going to fix what Copilot just wrote. And we're actually going to pull this in by doing ctx.bumps. And we're going to pull the bump of the treasury token account. Okay, and then we need the bump for the vesting account. So ctx.bumps.vesting account. Okay, and I spelled account wrong, so we'll just fix that typo. There we go. And then we're just returning an OK for our result. And that's everything we need for our first instruction. So you can see that most of the logic here happened within our create vesting account data structure because that's where all the accounts are handled. So if we go back down to our create vesting account, you can see we've set up both our vesting accounts and a token account for the treasury. And then the logic within the instruction is just saving all the information that we need to the account state of the vesting account. So first instruction is done. Now we can move on to the next. So not only do employers need to have a vesting account, but employees need to have a vesting account as well. And that's going to hold different information. It's going to hold all the information for their vested tokens, like the cliff time, how many tokens they have allocated to their public key, and anything associated with their token vesting. So that's going to be input by the employer of what their specific allocation is, and then the employee needs to be able to access that to be able to claim their tokens. So let's create the employee vesting account. Now, because we're creating a new account, let's define what is being saved to the state. We're going to do the same thing that we did with our vesting account by defining what the account is. So we'll use the account attribute that just tells that this is a Solana account. Okay. And then we're once again going to use derive init space because we need to calculate how much space it's going to take up on chain. Okay, and then we'll just define what this struct is. So this will be the employee account. So what do we want to save here? We want to know who's going to be able to claim this. So let's define what the beneficiary is. And that'll just be the public key of the employee for this specific account. So typically when you create a vesting account, you want to keep track of when the allocation started, when it's going to end, and what the cliff time is. So let's define all of that first. So the start time. Now this is all going to be stored in Unix time, which is an i64 type. The end time, also an i64, and then the cliff time. And what the cliff time is just how much an employee has to wait before any of their tokens unlock. And then once the cliff passes, it typically unlocks linearly after. Now, we'll also want to keep track of the vesting account. And this is just the corresponding vesting account that was just created by their employer. So that will be a public key because it will be the account address. And now we just need to know how many tokens are being allocated to the employee. So we'll do total amount, and that will be a U64 type. And then we want to keep track of how many the employee has withdrawn from their account. So we're able to calculate at a specific time how much they're able to either claim or how much they still have left to claim in the future. So total withdrawn. And that'll be a U64 type as well. Okay, so that's everything we're going to be storing to the state for the employee account. Now we can write the instruction to create this. So pub fn, and now we're going to create employee account. Okay, so we'll pass through the context as our first parameter, as always, when writing an anchor instruction. Define as a context type, and then we're going to create a data structure for create employee account. So let's pause from this instruction and go down here to write our derive accounts data structure. So pub struct create employee account. Add in our lifetime specifier. So now we want to know who the owner of this employee account is going to be. So the owner is actually going to be not the employee, but the employer, because the employer is going to be the person who has access to update the allocation information for a specific employee. So that's why we're going to update. The signer is going to be the owner. And once again, it needs to be mutable because we're creating an account, so the signer has to pay rent for that account. So we're going to set the signer as the owner. Okay, now we also need to know who the beneficiary is, which is the employee that's going to be able to claim tokens later on. So let's pass through the beneficiary account. And that'll be a system account. And we'll add in the lifetime specifier. Okay, now we need to pass through the vesting account. And that is because we're going to need all of the information from the vesting account state. But one thing we want to do is we want to use the has1 constraint to just make sure that the owner of the vesting account is the signer of this instruction. And that's just validating that the person with the correct access is going to be able to run this instruction. So we'll do the account attribute and add in the has1 constraint. and set that to owner. Okay, so now we have to actually create the employee account. So we're going to use, once again, the init constraint on the account. So account init. And this is just an account that is holding state, so we don't need to use the token constraint. And we're going to specify what the space is. We'll use the 8 discriminator from Anchor. And then we can just use a init space to calculate the rest. So employee account, a init space. And then because we're taking up space, we need to pay rent. So we need to define who the payer is. And then we're going to define the seats for our PDA. So here, let's use employee vesting. And then we're going to add in the beneficiary key as ref. And then the vesting account key as ref. And now that we have seeds, we also need a bump. And then all that's left is just to name what this account is. So it'll be our employee account. Okay, and now we have an error here. And that is because we need to define the system program whenever we're initializing a new account on chain. So we'll pass that through, and now our error went away. And that's everything we need for an employee account. So we can go back to the instruction and finish the logic there. Okay, so we'll load in the account the same way. We need to dereference, call the context accounts, and employee account this time. We'll use the employee account struct. Okay, and now we need the beneficiary is the first field. And that will just be the context accounts beneficiary key. And we have a typo, it's accounts with an S, there you go. And now we need the start time and the end time, but we don't know what that is. So we want to update our parameters to include start time and end time. And this will be passed on the front end. Okay, so we have our start time, we have our end time. Now we also need to pass through the total amount. So let's add that. That's a U64 type. Okay, and then the total withdrawn, since we're initializing a new account here, it's impossible to have withdrawn anything, so we'll just set that to 0. And then we need the cliff time, we'll pass through as a parameter. And now we need the vesting account, and we'll just pull in the account's vesting account key. And lastly, let's save the bump. Now this will be the bump of the employee account, so we can just do ctx.bumps employee account. Okay. And now we just need to return OK. So now we have an error, and it's saying there's no such field as bump, which means we forgot to define the bump in our employee account state. So we'll just go here and add that field because we always want to save the bump. There we go. So everything's good for creating an employee vesting account. Now, the last instruction that we need here is allowing the employee to come and claim tokens. So this will have a little bit more logic to make sure that an employee can claim tokens at the correct time. So let's start by defining this instruction. We'll do pub fn claim tokens. Okay, so we'll pass through the context as the first parameter, and then we'll go down and define what that is. So claim tokens. now we can do derive accounts for claim tokens. So this will pass through all of the accounts that are needed for an employee to be able to come to this program and claim tokens. So first we need the signer of the instruction. And in this case, instead of it being the owner of the vesting account, we want it to be the beneficiary of the employee account. So we'll update this to account. It needs to be mutable. And it will be the beneficiary, and that will be the signer of the instruction. And next we need the employee account. So we can define the account. And here we're going to need to update information in the account state because we'll be updating total withdrawn if an employee withdraws tokens. So we want to make the account mutable. And now we need the seeds. So this will be the same seeds from the employee account. So just to make things easier and make sure we have all of the correct information, we'll go back to when we initialize the employee account and just copy those seeds over. Okay, so this is employee vesting, the beneficiary, and the vesting account. And now we need the bump. And because we saved the bump when we were initializing, we're able to just pull that information. So we can do employee account dot bump. Now we're going to need to do 2 checks on this account. We want to make sure that it has the correct beneficiary, so only the employee that is the beneficiary of this employee account is able to come in and run the instruction claim tokens. And then we also want to make sure that this is connected to the correct vesting account that's being passed through. So we'll do has one beneficiary, and we'll also do has one for vesting account. Okay. So we'll just define this as the employee account. Now there's a few things here that we haven't defined yet. So the beneficiary was already passed through as the signer, but we need to define the vesting account. And the vesting account is used twice. So we want to just make sure that that account is passed through so it's able to pull the correct information. So let's pass through vesting account next. And we need the seeds for the vesting account. And we'll just do the same thing. We'll go back to when we initialize the vesting account and copy over the seeds. And then because we saved the bump to the vesting account state, we can just grab that information. And then we're going to do 2 checks here as well. So we want to make sure that this vesting account has the correct token account that's being passed through, and that is the treasury token account. So when this claim happens, it's going to be transferring SPL tokens from the treasury account into the employee token account. So we need to pass through the correct treasury account to be able to pull those tokens from. So we'll do has one and the treasury token account. And then we also want to make sure it has the correct mint address of the SPL tokens. So we'll do has one mint. So then we'll just define this account, and that's the vesting account. Now, there's a few things that we haven't defined yet. So one is the company name. Now we're going to have to pass through the company name as a parameter from the instruction. So let's go back up to the instruction, and let's add in company name here. And then for this data structure to be able to recognize that information, we have to pass through our instruction with the company name. Okay, so now you can see that error went away. Now we need both the treasury token account and the mint account to be passed through. So let's do the mint next. And that will be an interface account, mint. Now we need the treasury token account. So this also has to be mutable because we're going to be changing the token account balance. And all we have to do is just define what this is. So treasury token account, it's an interface account, token account. Okay. And now you can see both of those errors went away and all the accounts are passed through. Now, what else do we need? So we have the beneficiary, we have the employee account, we have the vesting accounts, we have the mint, and we have the treasury token account. So it seems like there's one important thing that's missing, and that is the employee token account. So we have the account state for the employee, but we don't have where the tokens are going to be sent to. So what we can do is create an associated token account. And this is where the init if needed constraint is going to come into play. So let's first define the account. And instead of init, we're going to use init if needed. And that's because some users may already have their token account for the specified SPL token created. And if they do, it's going to just bypass the init constraint and continue with the rest of the logic for the instruction. But if they don't already have this initialized, this account will then become initialized after running the instruction. Now we'll need the payer because it has init if needed. So if the user doesn't already have this account initialized, then we need a payer to be able to pay rent for the account. Okay, so in this case, the payer is going to be the beneficiary because it's their associated token account. Now we're going to just define what the associated token account is. So we'll use the associated token constraints. And first we want the mint, and that'll just be the mint address of the mint account that we're passing through. And then we also want the authority. And that'll be the beneficiary because it's their own token account. And then we also need to define the token program. So associated token, token program, and that will just be the token program. And now all that's left is to define what this account is, and this will be our employee token account. And because we're using the token interface, this will be an interface account, token account. Okay. Now, one thing is missing is what is the token program? So let's define that. And the token program is an interface, token interface. And now because we're using the associated token constraint, we also want to pass through the associated token program. And this is associated token. And then lastly, because we're potentially initializing a new account, we want to pass through the system program. Okay. And now that error went away. And this should be all of the accounts that are needed for claiming a token. But let's just double check. So we have our beneficiary, which is the signer. And we want to make sure that the beneficiary is the signer because we only want the beneficiary of the specified employee vesting to be able to claim tokens. And then we have the employee account, and that is just all of the state of this employee's vested token information. We're doing a check to make sure the correct beneficiary is signing, and also it's connected to the correct vesting account to grab the information for the mint and the company. Now we have the vesting account being passed through. We're checking the treasury token account is passed through correctly, and that's needed to be able to pull tokens from to send to the employee. And then we have the mint, which is to know what SPL token we're sending. Now we're passing through the mint account. We're passing through the treasury token account. And then we're creating, if needed, an employee token account, and that's the token account that's going to claim the SPL token for the vested token. And then just the token program, associated token program, and system program need to be passed through. Okay, so that looks like everything. Now we can go back to the logic needed to claim tokens. We can return the result. And I like to always, before writing all of the logic, just have our OK return value at the end so Rust doesn't get angry with us and have a bunch of errors as we're writing. First, we need to load in the employee account to get all of the information for the vested token. So let's load in the employee account. And here we're going to do a mutable reference. That is because we need to specify that the referenced account is going to change information. And let's do ctx accounts.employee account. Okay, so that loads in our employee account. It's being stated that it's a mutable reference. Now, earlier when we loaded accounts in, we used the dereference operator, but here we're using a mutable reference. So let's talk about the difference between the two as we're writing this out. So dereferencing is used when you need to manipulate the actual data stored in the reference location, and it's kind of less common at a high level operations, and it's mainly used when you're initializing or resetting account data. Earlier, we were initializing two accounts, so we were using the dereference operator. But here we're borrowing a mutable reference, and this allows you to pass employee accounts around in your function or to other functions while still having the ability to modify the original data. And this is useful when you're using multiple operations on the data, which we're going to be doing as we're calculating to be able to claim tokens. When you're claiming tokens, the first thing you want to know is the current point in time, so we can know if an employee is able to claim tokens or not. So let's first use the clock to figure out what the time is. So we'll do now is equal to clock.get, and we'll unwrap, and we need the Unix timestamp. Okay. Now we want to check if the current time is before the cliff time, because if it is before the cliff time, then no tokens can be claimed. So if now is less than the employee account dot cliff time, we want to return an error. And now we're going to create a custom error for this program. And we'll name it claim not available yet. And it's always important to define custom errors when you can, because it allows a user to understand more of why they're getting an error when they're interacting with the smart contract. So we can define custom errors by using the error code macro from Anchor. So we'll just do error code. So this error code attribute, it's applied to the enum that it's attached to generate a result type T or an error type. So that's used to return errors for the program. Okay, and we're using an enum here because you're only going to be calling one error at a time. Okay, so we'll do claim, We'll copy in the error that we specified just to make sure everything matches. Okay, and we can add a message that's going to be displayed for the user. So we'll do message, claim not available yet. There we go. And now you have a custom error in your program. Okay, so next we're going to have to start doing some calculations, but when you're running calculations in Rust, we have to add some additional checks. So we need to take into consideration both underflow and overflow errors. Underflow occurs when calculations result in a number that's smaller than the minimum value that can be stored in the data type. And overflow occurs in the reverse, when a calculation results in a number that's larger than the maximum value that can be stored in the data type. So we're going to use specific methods when we're writing out these calculations. So let's first calculate the amount of tokens that are able to be claimed. First, we're going to define the time since the start of the tokens being vested. So we'll do time since start And we'll do now. And instead of just subtracting, we're going to do a saturated sub. And what that does, it just ensures that the subtraction doesn't go below 0, which can help prevent underflow errors. So we'll do dot saturating sub. And we'll be subtracting the employee account start time. And this is an I-64 type because it's in Unix time. And now we need to find the total vesting time. So we'll do let total vesting time. And this will be the end time minus the start time, which gives you the total time period that the tokens are vested for the employee. So employee accounts dot end time. And we're going to subtract using saturating sub. And that will be subtracting the employee account start time. Okay. Now we're just going to do a little bit of error handling first. So we want to check to see that there is a total vesting time. So we're going to do if the total vesting time returns 0, then the vesting period was invalid for the employee. So let's just do that check first. So if total vesting time is 0, and this is also going to help with calculations in the future because we don't want to divide by 0 anywhere. So if total vesting time is 0, it will return an error. And we'll once again write a custom error code. So we'll do error code. Invalid vesting period, we'll call it. And now we'll just add that to our custom error enum. So we'll go down to the error codes enum and add invalid vesting period. And we'll add the message. Okay. And we'll go back to our instruction logic. Okay, so now we want to know the total vested amount of tokens, which is the total amount of tokens that the employee can claim. So we'll do let vested amount equal. Now, if the current time is after the end time, then all of the tokens have unlocked. So let's do a check for that. So if now is greater than or equal to the end time, then we're going to just return the total amount. And then else, we're going to do a match statement. And that's because we want to make sure that all of the calculations are safe and we're handling possible errors. So we're going to type it out like this. We'll do match, and then we'll take the total amount and multiply it by the time since start. So employee dot total amount. Employee account dot total amount and we're going to use checked multiply. So checked multiply is a multiplication, and the checked prefix allows you to handle possible overflow errors. So checked multiply and we're multiplying by the time since start. Because the time since start is an I-64 type because it's in Unix time, and the total amount is a U64 type, we're going to cast the I-64 as a U64. And you can do that by just typing as U64. because whenever you perform any calculation against variables in Rust, they have to be of the same type. Now, we'll do sum if the product of this multiplication we're just going to divide the product by the total vesting time. So what we're doing is we're taking the total amount, multiplying it by the time since start, and then dividing that by the total vesting time. Okay. And then if there's a none value. So the reason we're able to do this is because checked multiply, if there is an overflow error, instead of panicking, it returns a none value. So here we're just doing a check in our match statement. If it returns a value, we're going to be able to divide. If it returns a none, we're going to have to handle that error. We'll just return an error. And we'll make another custom error. And we'll name this one calculation overflow. And then we'll go back down to our error enum and add in the calculation overflow error and add a message. Okay. Okay, 1 second. My VS Code is being a little slow to update, so we'll just let that update. Okay, so just to recap this calculation, if we didn't perform a match statement here to check the product of your multiplication, then this checked mul is just going to return a none value, and then we wouldn't be able to do the division by the total vesting time. So by implementing the match statement, you're able to check to see if there's a product returned. And if there is, then you do the division. If there isn't, then you're handling the error of a none value being returned. Okay, so that looks good to me. Now we want to find what the claimable amount is for the user. So we found the vested amount. So this is how many tokens at the current point in time are unlocked. But if a user came in earlier and already claimed some, we want to be able to handle that. So what we're going to do is find the claimable amount by taking the vested amount and subtracting the total withdrawn value that's stored in the employee account state. So we can do let claimable amount So we'll do the vested amount, and then once again use saturating sub. And we'll do the employee account total withdrawn. Okay. And now a little more error handling. If the claimable amount is 0, we want to be able to let the user know that they have nothing to claim at the current point in time. So we'll do we'll do if claimable amount equals 0, then we're going to return an error of, and we'll do the error code, and we'll make a custom error called nothing to claim. And then we'll update our error code enum down here with our new custom error. So VS Code is being a little slow to update. All right, there we go. Now the error went away. now we did all the calculations needed. So we now know what the claimable amount is for the user. And now that we know what that is, we can actually process the claim. So by doing that, all we're going to be doing is a transfer of SBL tokens from the treasury account into the employee's token account. So we can do that by making a CPI call. A CPI call, it's a cross-program invocation, and it allows you to make calls from another program. In our case, the transfer is from the system program. So we can do let transfer CPI accounts, and we're going to define all the accounts needed for this transfer to take place. Here we're going to use transfer checked. And we want to make sure this has the correct import, which VS Code is once again still being slow. So instead of using the quick import, we're going to manually import. Looks like there was a weird import generated. Okay. So all we're going to do is update our token interface from the Anchor SPL crate to include transfer checked. Okay. Now we can go down here. And you can see from the structure, we need from, mint, to, and authority. So we'll define all of those fields. From, so the tokens are going to be coming from the treasury token account. So we'll load in the context account, treasury token account to account info. Now the mint is the next parameter, and we'll just do the mint account, and then we have to, and we have the authority. And in this case, the authority is going to be the treasury token account, and that is because when we earlier initialized the treasury token account, when we used the token constraint on the account attribute, we specified that the authority was itself. So here we can just set the authority to itself. Okay. So those are all the accounts that are needed for the transfer. Now we can define the CPI program. So let CPI program equal, and that is going to be the token program. So the transfer instruction that we're calling from the cross-program invocation is coming from the token program. The next thing we're going to have to do is define the CPI context. But first, to be able to sign the CPI context, we need to define what the signer is. And in our case, we had a PDA for the treasury token account. So we need to now derive that PDA to create our signer seeds. So let's do signer seeds. And the signer seeds have an interesting type, so we're going to explicitly define that type here. And all it is a few references. So 1, 2, 3, and a U8 type. Okay. So now we can go back to what our seeds were, which is for the treasury token account. When we created it, let's go to that context. Right here. So I'm just going to screenshot this so we can reference it and make sure we have the correct seeds. So we've first had our vesting treasury. Vesting treasury. And then the next field was the company name. So we can load that in from our context. So we can do context.accounts dot, and the company name was saved in our vesting account state. So we're going to use the vesting account. And then within the vesting account was the company name. And then lastly, we just need the bump defined. So we're going to reference the context.accounts. This is for the treasury accounts, and we saved the treasury bump into the vesting account state. So we're going to call in the vesting account, and then from that, we're going to pull in the treasury bump that we saved to the state. Okay, so one thing we were missing was adding a reference to the seeds. So we'll add that in. And now we'll just double check. We have our initial reference. We have the second reference for the seed. And then we have the last reference for the bump. Okay, and actually the bump lives inside of this. Okay, there we go. So now we have 3 nested references, and that is our signer seeds for the treasury token account. Now that we have that, we can define our CPI context. And this will be a CPI context new. And the first parameter is going to be the CPI program. And then we need the accounts. And now we need to specify that it's with signer because it is a PDA, so we need the signer of the PDA. So with signer, and this will be the signer seeds that we just derived. Now, lastly, we need the decimals of the SPL token that we're transferring. And that we can just take from the mint account that's passed through. So we can do context.accounts.mint. And then decimals. Okay. Now we can actually process this CPI. So we're going to use the token interface. And we'll do transfer checked. And we'll pass through the CPI context, the claimable amounts, and the decimals. And now let's make sure the claimable amounts is of a U64 type. So we'll just do, we'll cast as a U64. Okay, it looks like the signer seeds type may be off. So we're just gonna update the spacing here so it's easier to read. So we have our signing seeds, and we have our reference. Oh, okay, we're just missing a comma here. Here we go. Okay. Now we need to import the token interface. So the token interface is coming from the SPL token interface. We'll update the interface here. So this should just have self. Okay. Now we performed our CPI of transferring tokens from the treasury token account into the employee token account. And all we have left is just to update the account state for the employee to reflect that we've withdrawn tokens. So we'll add employee account dot total withdrawn and increment that by the claimable amount. And there we go. So that is everything for our instructions. Now, one thing to notice is in our parameters, we have company name and it's returning a warning. And that warning is because the company name is not being used within the instruction logic. But we need to tell Rust that we know it's not being used, but we're using it somewhere else. So to do that, we're just gonna add an underscore here. So just to recap, we've created vesting accounts for the employer. We've created employee accounts for the employee to be able to claim their allocated tokens. And we've created an instruction for employees to be able to come to the UI and grab the tokens that are claimable. So now let's do an anchor build to make sure that the program builds. So we need to remember to be in our anchor folder to do any instructions that are related to anchor.